Welcome to Triune Biblical University Global Extension USA channel. A warm welcome to all our returning subscribers and a heartfelt greeting to our new viewers. We're so glad to have you with us today. Whether you've been following us for a while or are just joining the community, we're excited to embark on this learning journey together. At Triune Biblical University Global Extension USA, we strive to provide valuable educational content that empowers you to grow, learn, and succeed. Your continued support and participation mean the world to us. In today's session, we are diving into lecture topic, where we'll explore important concepts and provide practical knowledge that you can apply in real-world scenarios. This lecture is designed to challenge your thinking and deepen your understanding, whether you're a beginner or an advanced learner. Thank you for joining us, and we hope you find today's lecture both insightful and inspiring. Let's get started. Chapter 10: Geosynthetics in Geotechnical Engineering. 10.1 Introduction to Geosynthetics. Geosynthetics are synthetic materials that are used in geotechnical engineering to improve the performance of soil, rock, and other natural materials in construction and infrastructure projects. These materials are designed to address a variety of engineering challenges, such as improving soil stability, enhancing drainage, providing reinforcement, and controlling erosion. Geosynthetics include a broad range of products, including geotextiles, geomembranes, geogrids, geocells, and geocomposites, each designed for specific applications. Geosynthetics are widely used in civil engineering projects like road construction, embankments, landfills, drainage systems, and slope stabilization, as they lower cost, effective and durable solutions to common geotechnical problems. Their application allows engineers to enhance the strength, durability, and environmental performance of geotechnical systems while reducing construction time and costs. In this section, we will explore the basics of geosynthetics, their various types, properties, and applications in geotechnical engineering. Understanding these materials is essential for making informed decisions on their use and maximizing their benefits in the design and construction of geotechnical systems. 10.1.1 Definition and types of geosynthetics. Geosynthetics are polymer-based materials, which means they are made primarily from synthetic polymers such as polyester, polyethylene, polypropylene, and PVC. These materials have a variety of functions depending on their specific design and properties. Below are the main types of geosynthetics and their applications in geotechnical engineering. 1. Geotextiles. Description. Geotextiles are permeable fabrics made from synthetic fibers that are used primarily for separation, filtration, reinforcement, drainage, and erosion control. Applications. Separation layers between different soil types to prevent mixing. Filtration and drainage systems to prevent clogging. reinforcement of weak soils or subgrades in roads and embankments. 2. Geomembranes. Description. Geomembranes are impermeable synthetic materials, typically made of polyethylene, PVC, or other materials used for sealing and lining. Applications. Applications. Lining for landfills, waste containment systems, and ponds to prevent leakage. Water reservoirs and canals to control seepage. 3. Geogrids. Description. Geogrids are grid-like materials made from polymers, typically used for reinforcement and improving the load-bearing capacity of soils. Applications. Reinforcing embankments, slopes, and road-based courses to improve stability. Reinforcement of retaining walls to enhance their strength and reduce deformation. 4. Geocells. Description. Geocells are three-dimensional cellular structures made from polymers used to provide confinement to soil or aggregate. Applications. Slope stabilization, erosion control, and load support in areas with weak or soft soils. Strengthening foundations by distributing loads over a wider area. 5. Geocomposites. Description. Geocomposites are combinations of different geosynthetic products, e.g., geotextiles combined with geomembranes or geogrids, designed to serve multiple functions in one product. Applications. Drainage systems, where both filtration and drainage are required. Landfill liners combining waterproofing and reinforcement properties. 10.1.2 Properties of geosynthetics. The properties of geosynthetics depend on the type of material and the intended application. The following are key properties of geosynthetics that influence their performance in geotechnical engineering. 1. Strength and steadiness. Geosynthetics, such as geogrids and geotextiles, are designed to provide strength and steadiness to weak soils. These materials improve soil stability by reinforcing the soil mass and distributing loads over a larger area. 2. Permeability. Geotextiles and geocomposites are used for drainage applications due to their permeability. They allow water to flow through while preventing the passage of soil particles, which helps in filtration and separation. 3. Durability and resistance to environmental conditions. Geosynthetics are designed to resist environmental factors such as UV, radiation, chemicals, and temperature extremes. Their durability ensures long-term performance in demanding applications like landfills, coastal engineering, and highway construction. 4. Elasticity and flexibility. Some geosynthetics, like geocells, are designed to be flexible and elastic, allowing them to conform to varying soil conditions and resist deformation. Underloading. 5. Chemical resistance. Geosynthetics used in waste containment or environmental applications. Need to be resistant to chemicals, leachates, and aggressive substances to prevent degradation and ensure longevity. 6. Compatibility with soil and other materials. Geosynthetics must be compatible with the surrounding soil and other materials used in the project. This ensures proper bonding and prevents failure due to incompatibility. 10.1.3 Functions and applications of geosynthetics. Geosynthetics are utilized in various applications to address specific geotechnical challenges. Below are the main functions and uses of geosynthetics in geotechnical engineering. 1. Separation. Geosynthetics are used to separate adherent soil layers, preventing mixing between subgrades and aggregate layers. This is particularly useful in road construction, where geotextiles prevent the intermixing of coarse aggregate with soft subsoil. 2. Reinforcement. Geogrids and geotextiles are used to reinforce weak or unstable soils, improving their bearing capacity and resistance to deformation. This is beneficial in projects like embankments, slopes, and retaining walls where additional strength is required. 3. Drainage. Geosynthetics are used to improve drainage by allowing water to flow through while filtering out soil particles. Geotextiles, geocomposites, and geomembranes are commonly used in drainage systems, such as beneath roads, landfills, and retaining walls. 4. Filtration. Geotextiles are employed in filtration applications, allowing water to pass through while preventing fine soil particles from migrating. This is essential in applications such as erosion control, septic systems, and drainage structures. 5. Erosion control. Geosynthetics such as geocells and geotextiles are used to control erosion on slopes, shorelines, and riverbanks by stabilizing the surface and reducing the impact of water flow. They prevent soil erosion while allowing vegetation to grow and further stabilize the area. 6. Containment. Geomembranes and geosynthetics are used for containment applications, such as lining landfills, waste storage areas, and ponds to prevent the leakage of liquids or gases into the surrounding environment. 7. Landfill liners and covers. Geosynthetics, particularly geomembranes and geocomposites, are used in landfill designs to prevent leachate leakage into the surrounding environment. They act as barriers to chemicals and other contaminants, ensuring that waste is safely contained. 8. Slope and foundation stabilization. Geogrids, geocells, and geotextiles are applied in slope stabilization and foundation strengthening, particularly in areas with weak or compressible soils. They prevent failure and reduce the risk of landslides or settlement. 10.1.4 Advantages of using geosynthetics. 1. Cost-effectiveness. The use of geosynthetics often leads to significant cost savings in construction projects. For example, their ability to stabilize soils and reduce the need for additional material layers can lower construction costs. 2. Ease of installation. Geosynthetics are relatively easy to install and can be applied quickly, reducing construction time compared to traditional methods. Their lightweight nature makes them easy to handle and transport. 3. Enhanced performance and durability. Geosynthetics improve the performance of geotechnical systems by providing long-term stability, reducing maintenance costs, and extending the life of the infrastructure. 4. Environmental benefits. Geosynthetics contribute to sustainability by reducing the environmental impact of construction. For example, they can help in managing stormwater, preventing soil erosion, and ensuring the containment of pollutants. 5. Versatility. Geosynthetics are versatile and can be used in a wide range of applications across various types of geotechnical projects, making them suitable for diverse environmental and engineering conditions. 10.1.5 Conclusion. Geosynthetics play an essential role in modern geotechnical engineering by addressing various challenges related to soil stability, drainage, reinforcement, and environmental protection. With a wide range of materials available, including geotextiles, geomembranes, geogrids, geocells, and geocomposites, engineers have versatile tools at their disposal to improve the performance and sustainability of infrastructure projects. The continued development and use of geosynthetics will likely lead to even more innovative and cost-effective solutions in the field of geotechnical engineering. Chapter 10: Geosynthetics in Geotechnical Engineering. 10.2 Types of geosynthetics and their applications. Geosynthetics are a broad class of materials that have become essential in geotechnical engineering for a variety of functions, including reinforcement, drainage, filtration, separation, and erosion control. These materials are primarily made from synthetic polymers, and their versatile nature allows them to address many engineering challenges. This section will explore the different types of geosynthetics and their specific applications. In the field of geotechnical engineering. 10.2.1 Geotextiles. Description: Geotextiles are permeable fabrics made from synthetic fibers such as polyester, polypropylene, or nylon. They are used in a wide range of applications to improve the mechanical properties of soils and prevent soil erosion. Geotextiles are typically manufactured in woven, non-woven, or knitted forms. Types: 1. Woven geotextiles, made by weaving synthetic fibers together, They provide high strength and are used in applications where high tensile strength is required. 2. Non-woven geotextiles, made by bonding fibers through heat, pressure, or adhesives. These geotextiles are often used for drainage and filtration due to their high permeability. 3. Knitted geotextiles. Created by knitting fibers into a mesh, these geotextiles are flexible and lightweight, commonly used for erosion control and reinforcement. Applications: 1. Separation. Geotextiles are placed between adherent soil layers, e.g., between subsoil and gravel, to prevent mixing and maintain structural integrity. 2. Reinforcement. Geotextiles are used to reinforce weak or unstable soils, such as in the construction of embankments, roads, and railways. 3. Filtration. Geotextiles act as filters in drainage systems, preventing fine particles from clogging drainage pipes or structures while allowing water to flow through. 4. Erosion control. Used on slopes, embankments, and riverbanks, geotextiles prevent soil erosion by stabilizing the surface and encouraging vegetation growth. 5. Road construction. Geotextiles improve the load-bearing capacity of road bases by reinforcing subgrade soils and preventing the mixing of soil and aggregate layers. 10.2.2 Geomembranes. Description: Geomembranes are impermeable synthetic materials made from polymers like polyethylene, polypropylene, and PVC. They are primarily used to prevent the movement of liquids or gases within or outside a geotechnical structure. Applications: 1. Landfill liners and covers. Geomembranes are widely used in landfill sites to contain hazardous or non-hazardous waste, preventing leachates from contaminating groundwater. 2. Water reservoirs and ponds. Used to line water storage facilities such as reservoirs, ponds, and canals to prevent water seepage. 3. Wastewater treatment plants. Geomembranes are used in various applications within wastewater treatment plants to line holding tanks or ponds to prevent the leakage of contaminated water. For containment of chemicals or leachates, they are used to prevent hazardous chemicals from leaking into the environment in industrial sites or hazardous waste facilities. 10.2.3 Geogrids. Description: Geogrids are polymeric materials designed to reinforce soils and improve the stability of structures. They are typically manufactured in a grid-like pattern, providing high tensile strength and the ability to spread loads over a large area. Applications: 1. Reinforcement of retaining walls. Geogrids are used to reinforce the soil behind retaining walls, increasing their load-bearing capacity and preventing failure. 2. Embankment stabilization. Geogrids are used in embankments and slopes to improve their strength and prevent settling or sliding of the structure. 3. Pavement reinforcement. In road construction, geogrids help in distributing the load more evenly, reducing pavement distress and extending the life of the roadway. 4. Base course reinforcement. Geogrids are used to reinforce the base course of roads, railways, and other paved areas, improving the overall performance of the pavement structure. 10.2.4 Geocells. Description: Geocells are three-dimensional, honeycomb-like structures made from polymer materials. When filled with soil, gravel, or other materials, they provide lateral confinement, improving the strength and stability of the material within. Applications: 1. Slope stabilization. Geocells are used to reinforce slopes, preventing erosion and soil displacement in areas where conventional methods might fail. 2. Erosion control. Geocells are installed on riverbanks, shorelines, or hillsides to reduce the effects of water erosion and provide long-term protection. 3. Load distribution. Geocells are used to distribute heavy loads over weak or soft soils, improving the load-bearing capacity of the ground. 4. Road and pavement construction. Geocells help reinforce the subgrade, providing additional support to roads and pavements, especially in areas with weak soils. 10.2.5 Geocomposites. Description: Geocomposites are multi-layered materials that combine different types of geosynthetics to provide a combination of functions. For example, a geocomposite may combine a geotextile for filtration with a geomembrane for impermeability, or a geotextile with a geogrid for reinforcement. Applications: 1. Landfill liner systems. Geocomposites combine geomembranes and geotextiles to create composite landfill liners, providing both filtration and containment properties. 2. Drainage systems. Geocomposites combine geotextiles and drainage layers, such as geomembranes or perforated pipes, for effective stormwater drainage, as seen in road construction or slope stabilization projects. 3. Pavement and road construction, used for reinforcement, drainage, and separation in roadway systems where multiple functions are required. 4. Reinforced soil systems. Geocomposites can combine geogrids or geotextiles with geomembranes to provide both soil reinforcement and drainage, improving the performance of retaining walls and embankments. 10.2.6 Geotubes. Description: Geotubes are large, tubular containers made from geotextile fabrics used to contain, dewater, and stabilize slurries and sediments. The fabric allows water to pass through while retaining solid particles. Applications: 1. Dewatering of slurry. Geotubes are used to dewater waste slurries, sediments, and sludge in landfills, construction sites, and sewage treatment facilities. 2. Shoreline protection. Geotubes are used in coastal engineering to protect shorelines from erosion by acting as barriers to wave action. 3. Sediment containment. They are used to contain sediments in dredging projects and prevent the contamination of surrounding waters. 10.2.7 Geocells for reinforced vegetated systems. Description: Geocells can be used as reinforcement structures for vegetated soil systems, where soil is confined within the cells, allowing plants to grow and stabilizing the surface. Applications: 1. Vegetative roofs. Geocells can be used in green roofs to reinforce soil layers and support plant growth, improving stormwater management and insulation. 2. Slope protection. Geocells are used for vegetative slope protection by providing soil stabilization and reducing erosion while allowing vegetation to thrive. 3. Soil stabilization for roads. In regions where soils are particularly soft, geocells help in stabilizing the soil, promoting vegetation growth, and enhancing load bearing capacity for unpaved roads. Conclusion: the various types of geosynthetics available today offer significant solutions to geotechnical challenges, from geotextiles used for filtration and reinforcement to geomembranes providing impermeable barriers and geogrids airing soil stabilization. Geosynthetics have become indispensable in modern geotechnical engineering. By understanding the types of geosynthetics and their applications, engineers can select the most appropriate material for specific site conditions and project requirements, ensuring better performance, sustainability, and cost efficiency in their projects. Chapter 10: Geosynthetics in Geotechnical Engineering. 10.3 Geosynthetics in Soil Reinforcement. Soil reinforcement is a critical aspect of modern geotechnical engineering, where the primary goal is to improve the strength, stability, and durability of weak or unstable soils. Geosynthetics play an important role in soil reinforcement by providing mechanical support to soil masses, enhancing their load-bearing capacity, and preventing failure. This section will explore the different ways in which geosynthetics are used to reinforce soils and improve engineering performance. 10.3.1 Mechanisms of Soil Reinforcement with Geosynthetics. Geosynthetics reinforce soils by distributing applied loads across a broader area and improving the overall strength of the soil. The mechanisms through which geosynthetics enhance soil reinforcement include: 1. Tensile resistance. Geosynthetics, such as geogrids and geotextiles, are designed to carry tensile forces, thus improving the soil's ability to resist deformation under loading. When these materials are embedded in soil, they act as a tension layer that resists stretching, helping to increase the overall stability of the soil. 2. Shear resistance. Geosynthetics provide shear strength to the soil by interlocking with soil particles. For example, Geogrids have a mesh-like structure that encourages the soil to grip onto the grid, preventing slippage and improving the overall shear resistance of the soil mass. 3. Lateral confinement. Geocells provide lateral confinement by enclosing soil particles within a three-dimensional structure. This confinement limits soil expansion under load, increasing the ejective stress and enhancing the soil's overall stability. 4. Stress distribution. Geosynthetics improve the load distribution within the soil. When incorporated into soil layers, these materials help to spread the applied load more evenly, thereby reducing stress concentrations and preventing failure. 5. Reinforcement through frictional resistance. Geosynthetics such as geotextiles and geogrids work by increasing the frictional resistance between soil particles. This increases the overall cohesion and friction within the soil, thus reducing the chances of displacement or failure. 10.3.2 Types of geosynthetics used for soil reinforcement. Several types of geosynthetics are commonly used for soil reinforcement, each varying unique benefits and applications based on the specific needs of the project. 1. Geogrids. Description. Geogrids are polymeric materials with a mesh-like structure designed to improve the mechanical properties of soils. They are typically used to reinforce granular soils and improve their load-bearing capacity. Applications. Geogrids are widely used in the construction of reinforced earth walls, steep embankments, and subgrade reinforcement in road and railway construction. Benefits. Geogrids provide excellent tensile strength, soil interaction, and long-term performance in a wide range of soil conditions. 2. Geotextiles. Description. Geotextiles are woven or non-woven fabrics made from synthetic polymers such as polypropylene and polyester. These fabrics can be used to reinforce soils by improving their drainage and filtration properties, as well as providing tensile strength. Applications. Geotextiles are used in various applications, including road construction, embankments, and slopes, where they reinforce and stabilize the underlying soil. Benefits. Geotextiles are flexible and easy to install, providing both reinforcement and drainage functionality. 3. Geocells. Description. Geocells are three-dimensional, honeycomb-like structures made from high-strength polymer materials. They provide lateral confinement to the soil, which improves its strength and load-bearing capacity. Applications. Geocells are used for stabilizing soft and weak soils, slope stabilization, erosion control, and foundation reinforcement in various civil engineering projects. Benefits. Geocells prevent soil erosion, improve compaction, and reduce differential settlement by distributing the applied load over a wider area. 4. Geocomposites. O. Description. Geocomposites combine two or more geosynthetics, e.g., geotextiles and geogrids or geotextiles and geomembranes to provide multiple functions such as drainage, reinforcement, filtration, and separation. O. Applications. Geocomposites are used in various applications where multiple geotechnical functions are needed, such as in landfill construction, roadways, and embankments. O. Benefits. They owe flexibility and cost-effectiveness by combining various properties, which can be tailored to specific engineering requirements. 5. Geotubes. O. Description. Geotubes are large, tubular containers made from geotextile fabrics used to reinforce soft soils. They are often filled with soil or sand to provide additional weight and stability. O. Applications. Geotubes are commonly used in coastal engineering, landfill reinforcement, and soft ground stabilization projects. O. Benefits. Geotubes are easy to transport and install, providing an efficient solution for reinforcing soft soils or areas prone to erosion. 10.3.3 Applications of geosynthetics in soil reinforcement. 1. Reinforced earth walls and slopes. O. Description. Reinforced earth walls are a common application of geosynthetics, where geogrids or geotextiles are used to stabilize the soil behind retaining walls and slopes. These materials help to improve the overall strength and prevent failure under the applied loads. O. Geosynthetics used. Geogrids, geotextiles, and geocomposites. O. Benefits. The use of geosynthetics in reinforced earth walls increases the stability of structures and allows for steeper slopes without the risk of failure. 2. Reinforced pavements and roadways. O. Description. In road construction, geosynthetics are used to reinforce the subgrade and subbase layers, which helps improve the overall performance of the pavement structure and reduce maintenance costs. O. Geosynthetics used. Geotextiles, geogrids, and geocomposites. O. Benefits. Geosynthetics increase the lifespan of roads by preventing the mixing of soil with aggregates, improving load distribution, and reducing settlement. 3. Slope reinforcement. O. Description. Geosynthetics are used to reinforce slopes and prevent soil erosion, especially in areas with weak or unstable soils. Geocells and geogrids are often used for slope stabilization. O. Geosynthetics used. Geocells, geogrids, geotextiles. O. Benefits. Geosynthetics improve slope stability, reduce soil erosion, and protect against landslides and other geohazards. 4. Embankments and dams. O. Description. Geosynthetics are widely used in the construction of embankments and dams to reinforce weak soils and improve the stability of the structure. They can be used for both vertical and horizontal reinforcement and embankment construction. Geosynthetics used: geogrids, geotextiles, geocomposites. Benefits: the use of geosynthetics reduces the need for expensive soil treatments and ensures long-term stability of embankments and dams. 5. Foundations and subgrade reinforcement. Description: geosynthetics are used to reinforce foundations, particularly in areas with soft or compressible soils, by improving the load distribution and preventing torrential settlement. Geosynthetics provide better stability for structures. Geosynthetics used: geogrids, geotextiles, geocells. Benefits: geosynthetics help to improve foundation performance, reduce settlement, and ensure the structural integrity of buildings and infrastructure. 10.3.4 Benefits of using geosynthetics in soil reinforcement. 1. Improve soil strength. Geosynthetics improve the tensile strength, shear resistance, and stability of soils, reducing the risk of failure under loading. 2. Cost-effectiveness. Geosynthetics are often more cost-effective than traditional reinforcement methods, such as deep foundations or soil stabilization techniques. 3. Reduce maintenance. By enhancing the performance of the reinforced soil, geosynthetics can reduce the frequency and cost of repairs and maintenance over time. 4. Environmental sustainability. Many geosynthetics are made from recyclable materials, which contribute to environmental sustainability and reduce the need for natural resources. 5. Versatility. Geosynthetics can be used in a wide variety of applications, including slope reinforcement, foundation stabilization, road construction, and more. Airing. Tailored solutions for specific site conditions. Conclusion: geosynthetics are an essential component in soil reinforcement, offering numerous advantages in terms of cost, efficiency, and sustainability. By improving soil strength, preventing failure, and enhancing the overall performance of geotechnical structures, geosynthetics have revolutionized the way engineers address challenging soil conditions. With their wide range of applications, geosynthetics continue to be a crucial tool for modern geotechnical engineering. Chapter 10: Geosynthetics in Geotechnical Engineering. 10.4 Geosynthetics in Drainage and Filtration Systems. Geosynthetics are widely used in drainage and filtration systems, providing effective solutions for managing water flow, controlling erosion, and improving soil stability. These materials play a key role in enhancing the performance of drainage systems in geotechnical applications, such as landfills, roads, embankments, and slope stabilization. By integrating geosynthetics into drainage and filtration systems, engineers can improve the longevity and functionality of these systems while minimizing maintenance requirements. 10.4.1 Role of geosynthetics in drainage systems. Drainage systems are critical in ensuring the proper flow and removal of excess water from construction sites, roads, slopes, and other infrastructure. Improper drainage can lead to soil erosion, foundation settlement, or structural damage. Geosynthetics, including geotextiles, geogrids, and geomembranes, are often used to improve water management and control groundwater seepage. 1. Water flow control. Geosynthetics help manage and direct the flow of water, ensuring that it is drained away from structures and areas at risk of water accumulation. This is essential for maintaining the stability of roads, foundations, embankments, and other structures built on or in soft soils. 2. Preventing soil erosion. In areas prone to erosion, geosynthetics such as geotextiles and geocells provide a protective layer over the soil, allowing water to pass through while preventing the loss of soil particles. This is particularly important for slopes, embankments, and riverbanks. 3. Reducing pore pressure. By allowing water to drain away from saturated soils, geosynthetics help reduce the pore pressure in the soil. This minimizes the risk of soil instability, particularly in areas subject to liquefaction or settlement. 4. Drainage layer in landfills. Geosynthetics are often used to construct drainage layers in landfills, where they help to collect and direct leachate, contaminated water, away from the landfill. This ensures that hazardous materials do not seep into the surrounding environment. 10.4.2 Types of geosynthetics used in drainage systems. Several types of geosynthetics are commonly employed in drainage systems, each serving specific functions in water management, filtration, and soil protection. 1. Geotextiles. Description. Geotextiles are synthetic fabrics made from woven or non-woven materials. They are commonly used for filtration and separation in drainage systems, allowing water to pass through while preventing the migration of fine soil particles. Applications. Geotextiles are used in various drainage applications such as road subbases, embankment stabilization, and landfill drainage. They are also used in French drains, drainage pipes, and surface water control. Benefits. Geotextiles help in providing filtration while maintaining soil structure and preventing clogging. They are also flexible, easy to install, and cost-effective. 2. Geogrids. Description. Geogrids are polymeric grids that are used in drainage applications for providing reinforcement, improving the stability of drainage structures, and preventing soil displacement. Applications. Geogrids are commonly used in road construction, embankments, and landfill drainage systems, where they help to control soil movement, and enhance water drainage. O benefits. Geogrids improve the structural integrity of drainage systems by preventing deformation under load while promoting water movement through the soil. 3. Geomembranes. O description. Geomembranes are impermeable synthetic liners made from materials such as polyethylene or PVC. They are used to prevent the passage of water or other liquids through soil and are critical in applications requiring containment or water isolation. O applications. Geomembranes are typically used in landfills, pond liners, and waterproofing applications. They can also be used in combination with drainage systems to isolate water from contaminants or to control the movement of water in underground reservoirs. O benefits. Geomembranes provide reliable waterproofing and containment, making them ideal for managing hazardous materials, leachate collection, and groundwater protection. 4. Drainage composites, geocomposites. O description. Geocomposites combine different geosynthetic materials, such as geotextiles and drainage cores, to form composite products that serve multiple functions, such as drainage, filtration, and separation. O applications. Geocomposites are used in a wide range of applications, including road construction, retaining walls, embankments, and landfill drainage systems, where they provide a combination of drainage and filtration capabilities. O benefits. Geocomposites, an efficient solution for complex drainage problems, as they combine the best properties of multiple geosynthetics in a single product. They improve water flow while preventing clogging in soil migration. 10.4.3 Geosynthetics and filtration systems. Filtration is a critical function in drainage systems, as it prevents soil particles from clogging the drainage channels, which could otherwise reduce the efficiency of the system. Geosynthetics play a vital role in filtration by allowing water to pass through while retaining fine soil particles. 1. Filtration through geotextiles. Geotextiles are used to filter water passing through drainage systems, as they allow the free flow of water while retaining soil particles, preventing clogging and ensuring long-term performance of drainage systems. These materials are commonly placed in road subgrades, slopes, and embankments. 2. Filtration in landfill applications. In landfills, geotextiles are used as filters to ensure that leachate flows through the drainage system without allowing fine particles to enter the underlying soil or groundwater. Geotextiles can also be used to prevent the mixing of different soil types in landfill drainage systems. 3. Prevention of clogging. Geotextiles and drainage composites provide a permeable barrier that reduces the likelihood of clogging. They prevent the migration of fine soil particles while allowing water to flow through freely, ensuring that the drainage system remains effective over time. 4. Improve drainage efficiency by incorporating geosynthetics into filtration systems. Engineers can maintain the efficiency of drainage systems over the long term. The ability of geotextiles and other geosynthetics to filter water without clogging enhances the performance and reliability of the system. 10.4.4 Applications of geosynthetics in drainage and filtration systems. 1. Road construction and pavement drainage. Geosynthetics such as geotextiles and geocomposites are used to improve the drainage of roads and pavements, preventing water accumulation and ensuring proper water flow away from the surface. They are placed in subgrades, subbases, and base layers to enhance the performance of the drainage system. 2. Landfill drainage systems. Geosynthetics, particularly geomembranes, are used in landfills to contain leachate and prevent contamination of surrounding soil and groundwater. Geotextiles and geocomposites are used to facilitate proper drainage while preventing the infiltration of contaminants. 3. Slope stabilization and erosion control. Geosynthetics are used in slope stabilization applications to prevent erosion and improve drainage. Geotextiles, geocells, and geocomposites provide both filtration and drainage while protecting slopes from soil loss. 4. Drainage for retaining walls and embankments. Geosynthetics are used to improve the drainage behind retaining walls and embankments, preventing water accumulation that could lead to instability. Geotextiles or drainage composites are placed in these areas to ensure effective water flow and reduce the risk of structural failure. 5. Coastal and waterfront projects. Geosynthetics are used in coastal engineering projects such as seawalls, jetties, and embankments to control water flow, prevent erosion, and improve drainage. They are especially useful in areas prone to high moisture or where groundwater control is crucial. 10.4.5 Benefits of geosynthetics in drainage and filtration systems. 1. Improved water flow. Geosynthetics provide reliable drainage solutions by enhancing water flow through soils, reducing the risk of waterlogging and improving the longevity of structures. 2. Cost-effective. The use of geosynthetics in drainage and filtration systems is often more economical compared to traditional methods, such as gravel or sand filters, while offering similar or superior performance. 3. Prevention of clogging. Geosynthetics act as filters, preventing the migration of fine particles that can clog drainage systems, ensuring their efficient operation over time. 4. Durability. Geosynthetics are highly durable and resistant to weathering, ensuring long-term performance and minimal maintenance in drainage and filtration systems. 5. Versatility. Geosynthetics can be used in a wide range of applications from roadways to landfills to slopes, airing flexibility in design and function for various drainage and filtration needs. Conclusion: geosynthetics play a critical role in the design and implementation of drainage and filtration systems in geotechnical engineering. These materials provide effective solutions for controlling water flow, reducing soil erosion, and maintaining the stability of structures. By incorporating geosynthetics into drainage and filtration systems, engineers can improve the performance and sustainability of these systems, contributing to the long-term success of infrastructure projects. Chapter 10: Geosynthetics in Geotechnical Engineering. 10.5 Environmental and Sustainability Considerations. The use of geosynthetics in geotechnical engineering is expanding due to their numerous advantages, such as improving performance and reducing construction costs. However, it is also important to assess the environmental impact and sustainability of these materials in order to ensure that their benefits are realized without compromising ecological and societal interests. Geosynthetics are made from synthetic polymers, primarily petroleum-based, which presents a number of environmental challenges that need to be addressed in their life cycle. 0.5.1 Environmental impacts of geosynthetics. 1. Production and manufacturing. Geosynthetics are typically made from petroleum-based polymers such as polypropylene, polyethylene, and polyester. The production process of these materials involves energy consumption and the release of greenhouse gases, contributing to environmental pollution. Furthermore, raw material extraction, such as petroleum, has additional environmental impacts, including habitat disruption and pollution. 2. Non-biodegradability. Most geosynthetic materials are not biodegradable. Once disposed of, they persist in the environment for long periods. This can contribute to waste accumulation, especially in landfills or in cases where geosynthetics are not recycled properly. If geosynthetics enter ecosystems through improper disposal or accidental release, they can contribute to plastic pollution, particularly in aquatic environments. 3. Manufacturing waste. The production of geosynthetics often generates waste materials, such as scraps from manufacturing processes. If not properly managed, this waste can contribute to environmental degradation. Additionally, the production of geosynthetics may involve the use of chemicals and additives that have their own environmental and health impacts. 4. Energy consumption. The energy required to produce geosynthetic materials, including the raw materials and manufacturing processes, is significant. This energy consumption can have a substantial environmental impact, particularly if the Energy used is derived from non-renewable sources. 10.5.2 Sustainability considerations in geosynthetics. 1. Recycling and reuse. To reduce the environmental impact, efforts are being made to increase the recyclability of geosynthetics. Some geosynthetics, such as certain types of geotextiles, can be recycled and reused in future construction projects. Recycled materials reduce the need for virgin resources and can help minimize the environmental footprint associated with geosynthetic production. Closed-loop recycling. Closed-loop recycling allows for the reuse of geosynthetic materials in the same type of applications. For example, geotextiles used in road construction can be recycled and reused in similar drainage or filtration applications. Upcycling. In some cases, geosynthetics can be upcycled, meaning they are repurposed for new applications that can provide higher value or extended service life. For example, used geotextiles from one project might be reused in landscaping or erosion control. 2. Biodegradable alternatives. In response to the environmental concerns regarding non-biodegradability, researchers are working on developing more sustainable geosynthetic materials that are biodegradable or made from renewable resources. 4. Instance. Some geotextiles have been developed using natural fibers like jute or core, which are biodegradable and have a lower environmental impact. Bio-based polymers. Some manufacturers are developing bio-based geosynthetics made from plant-derived polymers, which can be more sustainable and environmentally friendly than petroleum-based polymers. These alternatives are designed to degrade over time or to be produced from renewable sources, reducing the ecological footprint. 3. Environmental Product Declarations, EPDs. The use of environmental product declarations, EPDs, has increased to allow engineers and project stakeholders to assess the environmental impact of geosynthetic products. EPDs provide information about the life cycle environmental performance of materials from production through disposal. They help identify products with lower carbon footprints, reduced energy consumption, and minimal environmental impact, allowing for more informed decisions regarding material selection. 4. Green building and sustainable construction. Geosynthetics contribute to sustainable construction practices by improving the durability and longevity of infrastructure projects. For example, the use of geosynthetics in road construction can reduce the need for frequent repairs, which decreases the overall environmental impact. Additionally, by improving drainage, geosynthetics help to prevent erosion and waterlogging, which can be environmentally damaging. LEED certification. Some geosynthetic products can contribute to sustainable building certification systems, such as the Leadership in Energy and environmental design LEED certification. Products with low environmental impacts, including those made from recycled materials or those contributing to energy efficient construction practices, can earn LEED points and enhance the sustainability of a project. 5. Waste minimization. The use of geosynthetics can help minimize construction waste. 4. Instance, the durable nature of geosynthetic materials means that infrastructure projects require fewer repairs, replacements, or upgrades over time. This reduces the volume of construction waste generated during the life of a project. Additionally, because geosynthetics are often lighter than traditional construction materials, such as gravel or stone, they can reduce the overall material demand and associated waste. Their long service life and durability help minimize the need for new materials and reduce construction-related environmental impacts. 10.5.3 Environmental benefits of geosynthetics. Despite their environmental challenges, geosynthetics also offer numerous environmental benefits when properly managed. 1. Reduction of erosion. Geosynthetics such as geotextiles and geocells are commonly used for erosion control in vulnerable areas like slopes, riverbanks, and embankments. These materials protect against soil loss, preventing downstream sedimentation and maintaining ecosystem health. 2. Water conservation. By improving drainage and water management systems, geosynthetics contribute to more efficient water use in construction projects. The ability of geosynthetics to promote water flow and manage groundwater can be crucial in arid regions or areas with limited water resources. 3. Sustainable infrastructure. The durability and longevity of geosynthetics reduce the need for frequent maintenance and repairs, leading to a more sustainable infrastructure over time. For example, geosynthetics used in foundation systems can reduce settlement and prevent structural failures, minimizing the need for costly and environmentally disruptive repairs. 4. Energy efficiency. By improving soil stability and preventing erosion, geosynthetics can help reduce the energy required for maintenance and rehabilitation. This is particularly significant in the case of roadways, embankments, and landfills, where energy-intensive repair and reclamation efforts are often required. 10.5.4 Strategies for enhancing sustainability in geosynthetics. 1. Developing eco-friendly materials. Research and development into biodegradable geosynthetics and the use of renewable resources in production is essential to minimize the environmental impact. The adoption of sustainable practices in manufacturing can significantly reduce the environmental footprint of these materials. 2. Increasing recyclability. Encouraging the recycling of geosynthetic materials can help close the loop on material life cycles and reduce waste. Recycling initiatives, both in construction projects and in industrial settings, can help ensure that geosynthetics are reused and repurposed efficiently. 3. Sustainable product design. Geosynthetics can be designed to meet sustainability criteria, focusing on minimizing raw material use, reducing manufacturing emissions, and extending the service life of the product. This can help ensure that these materials contribute to the long-term sustainability of infrastructure projects. 4. Adopting circular economy principles. A circular economy approach encourages the reuse and recycling of materials at the end of their life, as well as reducing waste. Implementing these principles for geosynthetics can lead to a more sustainable life cycle for these materials, reducing their environmental impact. Conclusion: geosynthetics offer significant environmental benefits when properly designed, produced, and managed. By reducing soil erosion, improving drainage, and enhancing the longevity of infrastructure, these materials contribute to more sustainable geotechnical engineering practices. However, their environmental impact, particularly in terms of resource use and waste generation, should not be overlooked. The development of biodegradable geosynthetics, recycling initiatives, and eco-friendly manufacturing processes will be crucial in minimizing the negative environmental effects of these materials, ultimately leading to a more sustainable and responsible approach to geotechnical engineering. Chapter 11: Ground Improvement Techniques. 11.1 Soil Stabilization Methods. Soil stabilization is a key ground improvement technique used in geotechnical engineering to enhance the strength, durability, and workability of soils. By modifying the properties of weak or problematic soils, stabilization methods can make them more suitable for construction purposes. These techniques are crucial in areas with soft, expansive, or loose soils where the soil cannot support the desired loads or is prone to excessive settlement. There are various soil stabilization methods, each with its own set of advantages and specific applications. This section outlines the most common soil stabilization techniques used in geotechnical engineering. 1.1.1 Mechanical stabilization. Mechanical stabilization involves modifying the soil's properties through physical processes that alter its composition and structure. This method is often used to improve the load-bearing capacity and reduce soil movement. 1. Compaction. Compaction is the process of increasing the density of the soil by reducing the voids between soil particles. This is typically achieved by applying mechanical energy through rollers, vibrating plates, or tamping tools. Purpose. The goal is to increase the soil's shear strength and reduce its compressibility. Compaction is often used in the construction of embankments, foundations, and roadways. Applications suitable for granular soils like sand, gravel, and crushed stone. 2. Grading. Grading is the process of adjusting the particle size distribution of the soil to optimize its compaction and drainage properties. By adding larger particles, such as gravel or finer materials like clay, the soil can be better compacted and more stable. Purpose. This method helps to improve the soil's overall strength and reduce the risk of settlement. Applications. Common in road construction and base layers for pavements. 3. Vibrocompaction and dynamic compaction. Vibrocompaction involves the use of a vibrator to compact loose sandy soils. The vibration helps to rearrange the soil particles, reducing voids and increasing soil density. Purpose. It enhances the load-bearing capacity of the soil and improves its resistance to liquefaction. Applications. Used in areas with loose sand or granular soils, especially for foundations or infrastructure. 1.1.2 Chemical stabilization. Chemical stabilization involves the use of chemical additives or binders to improve the physical properties of the soil, such as its strength, durability, and resistance to moisture. This technique is often applied to fine-grained soils, such as clays or silts, which are more difficult to compact and stabilize through mechanical means. 1. Cement stabilization. Cement is mixed with the soil to improve its strength, reduce plasticity, and lower its permeability. The process involves adding a specified amount of cement and mixing it with the soil, followed by compaction. Purpose. Cement stabilization improves the shear strength and reduces the swelling and shrinkage behavior of expansive soils. Applications. Used for stabilizing clayey soils, subgrades for roads, and foundation beds for buildings. 2. Lime stabilization. Lime is commonly used to stabilize fine-grained soils, especially clays. It reacts with the clay minerals to form cementitious compounds that improve the soil strength and workability. Purpose. Lime stabilization reduces soil plasticity, improves compaction, and increases shear strength. Applications. Frequently used for road construction, embankments, and in regions with expansive clays. 3. Fly ash stabilization. Fly ash, a byproduct of coal combustion, can be mixed with soil to improve its strength and reduce its permeability. It reacts with the soil to form cementitious compounds that enhance soil stability. Purpose. Fly ash stabilization is cost-effective and environmentally friendly, making it an excellent option for improving soil properties in large-scale infrastructure projects. O applications, often used for stabilizing silts, clays, and soft organic soils in road construction, embankments, and landfills. 4. Polymer stabilization. O polymers, such as polyurethane, are sometimes used to stabilize soils by creating a chemical bond between soil particles. O purpose, polymer stabilization improves the durability of the soil and makes it more resistant to water erosion, swelling, and shrinkage. O applications, commonly used in areas where long-term soil stability is required, such as for highway construction or industrial sites. 5. Bituminous stabilization. O bitumen or asphalt is mixed with soil to improve its resistance to water and its strength. This technique is often used in road construction to create a waterproof and durable base. O purpose, it reduces the soil's permeability and enhances its stability, especially in areas with high moisture content. O applications, typically used for road subgrades and bases, particularly in wet or coastal regions. 1.1.3 Biological stabilization. Biological stabilization methods involve the use of plants or microbial agents to stabilize soil. These methods are environmentally friendly and are gaining popularity for their sustainability and low environmental impact. 1. Phytoremediation. O phytoremediation involves planting vegetation, particularly deep-rooted plants, to improve soil stability. The roots help to bind the soil particles together, reducing erosion and promoting soil structure. O purpose, this method enhances the soil's resistance to erosion, stabilizes slopes, and can also help with the absorption of contaminants from the soil. O applications, common in areas prone to erosion, such as steep slopes, embankments, and riverbanks. 2. Microbial-induced carbonate precipitation, MICP. OMICP is a biotechnological process that uses bacteria to induce the precipitation of calcium carbonate in the soil, thereby improving its strength and stability. O purpose, this method is environmentally friendly and can enhance the shear strength of the soil, making it more resistant to liquefaction, erosion, and settlement. O applications, useful in strengthening weak soils and improving the foundation of structures in areas where chemical stabilization is not feasible. 1.1.4 Thermal stabilization. Thermal stabilization involves the use of heat to alter the properties of certain soils, particularly those containing expansive clay minerals. By applying heat, the soil's moisture content is reduced, and its physical properties are modified to make it more stable. 1. Electrical resistivity heating. O electrical resistivity heating involves applying an electric current through soil to heat it. This method is used to modify the moisture content and stabilize soils in areas with problematic expansive clays. Purpose. The heat reduces the soil's volume changes and stabilizes its structure. Applications. Common in areas with highly expansive clays or soils prone to significant volume changes with moisture fluctuations. 1.1.5 Grouting techniques. Grouting is the injection of fluid materials, such as cement-based mixtures, into the soil to improve its strength, reduce permeability, and stabilize it for construction. This technique is often used for deep soil improvement or to seal areas with water ingress problems. 1. Cement grouting. Cement grouting involves injecting a cement slurry into the soil to form a solidified mass that increases the soil's strength and reduces its permeability. Purpose. It is used for stabilizing loose soils, reducing groundwater flow, and increasing the load-bearing capacity of the ground. Applications. Often used in foundation work, soil consolidation, and sealing. Groundwater flows in tunnels or dams. 2. Chemical grouting. Chemical grouting involves the injection of chemical solutions, such as sodium silicate or polyurethane, into the soil. These chemicals react with the soil to form a gel-like substance that binds soil particles together. Purpose. It enhances soil strength and decreases its permeability, making it more resistant to erosion and settlement. Applications. Useful for stabilizing loose sands, silts, and soft soils, and for controlling groundwater flow in underground structures. Conclusion. Soil stabilization techniques are essential for improving the properties of problematic soils, making them suitable for construction. Each stabilization method, whether mechanical, chemical, biological, thermal, or through grouting, offers unique benefits and applications. The selection of the most appropriate technique depends on factors such as soil type, project requirements, environmental considerations, and cost-effectiveness. With the continuous development of new technologies and materials, the effectiveness and sustainability of soil stabilization methods continue to improve, helping geotechnical engineers design safer and more durable structures. Chapter 11. Ground Improvement Techniques. 11.2 Deep Soil Mixing and Vibrocompaction. Ground improvement techniques such as deep soil mixing and vibrocompaction are critical methods for enhancing the properties of problematic soils. These techniques are typically applied to weak or unstable soils that require significant improvement to support structures or construction projects. Both deep soil mixing and vibrocompaction play a key role in geotechnical engineering, offering solutions to increase soil strength, reduce settlement, and improve overall ground stability. Below, we explore both techniques in detail. 1.2.1 Deep Soil Mixing, DSM. Deep soil mixing, DSM, is a ground improvement technique in which binders, usually cement, lime, or other stabilizing agents, are introduced into the soil at depth by mixing them with the native soil. This process creates a more stable and stronger soil structure, which is suitable for construction purposes. The technique involves the use of specialized equipment to mix soil and binder materials at specific depths, creating improved soil columns or blocks. 1.1.2.1.1 Process of deep soil mixing. 1. Soil mixing. The process starts with a mixing tool, typically a set of augers or a rotating blade, being driven into the soil at the desired depth. These tools mix the soil with the binder, cement or lime to create a solidified column or block of improved soil. The binder is typically injected in slurry form during the mixing process to ensure uniform distribution. 2. Binder injection. The binder is injected under pressure, ensuring proper mixing and chemical reaction with the soil. Common binders include cement, lime, or a combination of both, depending on the soil type and the required strength. Properties. 3. Columns or slabs formation. The soil and binder mixture creates columns or slabs, also known as soil cement columns, within the soil mass. These columns serve as the improved, load-bearing zones that reinforce the overall ground structure. 1.1.2.1.2 Applications of deep soil mixing. Foundation improvement. DSM is particularly useful for improving the bearing capacity of soils for foundations. The process is used for soft soils, loose sands, silts, or highly compressible clays that would otherwise not support heavy structures. The columns formed by deep soil mixing act as reinforcement to distribute loads evenly, reducing the risk of excessive settlement and improving the overall stability of the foundation. Liquefaction mitigation. In regions prone to seismic activity, DSM can be employed to mitigate liquefaction risks. By reinforcing the soil with deep soil mixing columns, the soil's resistance to liquefaction is enhanced, making it more stable during earthquakes. Slope stabilization. DSM is used to stabilize slopes and prevent landslides in areas with weak soils. The deep mixing columns reinforce the soil mass, reducing the risk of slope failure due to increased strength and cohesion. Contaminated soil remediation. DSM is also used in the remediation of contaminated sites. By incorporating stabilizing agents, the technique can reduce the mobility of contaminants in the soil and prevent further spread of pollutants. 1.1.2.1.3 Advantages of deep soil mixing. Improves strength and stability. DSM improves the shear strength and bearing capacity of soils, making them suitable for supporting heavy structures. Reduce settlement. The columns created by DSM help reduce settlement under load, providing a stable foundation. Environmental benefits. DSM can be an environmentally friendly technique, especially when lime or other non-toxic binders are used. It can also be applied in contaminated soil. Areas to reduce environmental hazards. Versatility. DSM is highly effective in a variety of soil types, including soft clays, silts, and loose sands, which are otherwise challenging to improve using traditional methods. 1.2.2 Vibrocompaction. Vibrocompaction, also known as vibroflotation, is a ground improvement technique used to densify loose granular soils such as sands and gravels. This method uses vibration to rearrange the soil particles, reducing the voids between them and increasing the soil's density. The result is a more stable ground, capable of supporting larger loads and reducing settlement. 1.2.2.1 Process of vibrocompaction. 1. Vibration probe. The process involves a large vibrating probe, often called a vibroflot, being lowered into the ground. The vibroflot produces intense vertical vibrations that penetrate deep into the soil. 2. Soil compaction. As the vibroflot vibrates the soil particles are rearranged and compacted. The process effectively reduces the void ratio between the particles and increases the density of the soil. 3. Soil improvement. The vibroflot is raised in stages while continuing to vibrate the soil, allowing for incremental densification at different levels. In some cases, the process is combined with the injection of water, air, or grout to further improve the soil's characteristics. 4. Completion. Once the compaction process is complete, the vibroflot is removed, and the ground is left with improved density and stability. In some cases, densification may be verified by measuring the soil's relative compaction or by conducting field tests, such as the Standard Penetration Test, SPT, or Cone Penetration Test, CPT. 1.2.2.2 Applications of vibrocompaction. Improvement of loose sands. Vibrocompaction is especially effective in improving loose sandy soils that are prone to liquefaction or excessive settlement. By densifying these soils, vibrocompaction increases their load-bearing capacity and makes them more resistant to seismic activity. Prevention of liquefaction. In areas subject to seismic activity, vibrocompaction is used to reduce the risk of liquefaction by densifying loose granular soils, which helps to prevent soil failure during an earthquake. Foundation and roadway construction. Vibrocompaction is widely used in the construction of roads, embankments, and foundations, where dense soils are required to support the weight of structures and vehicles. Reclamation of land. The technique is commonly used in land reclamation projects to improve the stability of sandy soil or reclaimed land, ensuring that it can support future construction. 1.1.2.2.3 Advantages of vibrocompaction. Increased density and strength. Vibrocompaction significantly increases the density of loose granular soils, thereby improving their strength and stability. Reduce settlement. The technique helps to reduce both immediate and long-term settlement of structures by densifying the soil, making it more resistant to deformation. Underload. Liquefaction mitigation. By densifying soils, vibrocompaction reduces the risk of liquefaction in areas subject to earthquakes, ensuring safer construction in seismic zones. Cost-effectiveness. Vibrocompaction is often more cost-effective compared to other methods of ground improvement, especially for large-scale projects involving loose, granular soils. Minimal environmental disruption. The process of vibrocompaction generally causes minimal environmental disruption compared to other soil improvement techniques. It is a relatively non-invasive method, and the vibrations can be controlled to minimize the effects on surrounding structures. 1.2.3 Comparison of deep soil mixing and vibrocompaction. Feature deep soil mixing, DSM, vibrocompaction. Soil types. Effective for cohesive soils, clays, silts, and granular soils. Primarily used for granular soils, sands, gravels. Applications. Foundation improvement, slope stabilization, liquefaction mitigation. Roadways, embankments. Seismic hazard mitigation. Improvement. Mechanism. Soil cement columns formed by mixing binders with native soil. Densification of granular soils through vibration. Binder material cement, lime, fly ash, etc. No binders used. EECT on soil. Increases shear strength, reduces permeability, prevents settlement. Increases soil density. Improves load bearing capacity. Environmental impact. Can be environmentally friendly if non-toxic binders are used. Minimal environmental disruption, non-invasive. Depth of treatment. Can treat deep soil layers up to 30 meters or more, typically up to 20 meters. Feature deep soil mixing, DSM, vibrocompaction. Speed of application. Slower process due to mixing and curing time. Faster compared to other techniques. Cost. Can be more expensive due to binder costs and machinery. Generally cost-effective for large-scale projects. Conclusion. Both deep soil mixing, DSM, and vibrocompaction are essential ground improvement techniques that owe unique advantages for enhancing the properties of weak or unstable soils. While DSM is primarily used for improving cohesive soils and providing a solid foundation for structures, vibrocompaction is most effective in densifying loose granular soils, particularly in seismic zones. The choice of technique depends on the soil type, project requirements, and specific ground conditions, and both methods contribute significantly to ensuring the stability, safety, and durability of construction projects. Chapter 11: Ground Improvement Techniques. 11.3 Grouting Techniques in Geotechnical Engineering. Grouting is a ground improvement technique that involves injecting a fluid or semi-fluid material, called grout, into soil or rock formations to enhance their properties. The injected grout fills voids, cracks, and fractures in the soil or rock, improving their strength, stability, permeability, and other geotechnical characteristics. Grouting is widely used in various geotechnical engineering applications, including foundation support, soil stabilization, seepage control, and tunnel construction. In this section, we explore the different types of grouting techniques used in geotechnical engineering, their applications, processes, and advantages. 1.3.1 Types of grouting techniques. Grouting techniques can be classified into various types based on the materials used and the objectives of the process. Below are the main types of grouting techniques commonly used in geotechnical engineering. 1.3.1.1 Permeation grouting. Permeation grouting involves injecting grout into soil to fill the voids and permeate the pore spaces between the soil particles. The goal is to reduce the permeability of the soil or improve its strength and stability by filling the voids with a solidifying grout. Materials used: cement-based grouts, chemical grouts, e.g., sodium silicate, polyurethane. Applications: groundwater control, seepage prevention, foundation strengthening. 1.3.1.2 Compaction grouting. Compaction grouting involves injecting a thick grout mixture into the ground to displace and compact the surrounding soil, thereby increasing its density and improving its load bearing capacity. The grout is injected under pressure, causing the soil particles to shift and compact as the grout displaces the soil. Materials used: cement-based grout with varying degrees of viscosity, low mobility grout. Applications: soil densification in loose or soft soils, stabilization of weak or compressible soils, foundation support for structures. 1.3.1.3 Jet grouting. Jet grouting uses high-pressure grout jets to erode the soil and mix it with the grout, creating solidified soil cement columns. The technique is used to treat deep soils and is effective in both cohesive and non-cohesive soils. Jet grouting can be performed at depths ranging from shallow to very deep levels. Materials used: cement-based grouts, bentonite slurries, chemical additives. Applications: waterproofing and seepage control, soil stabilization, foundation reinforcement, excavation support. 1.3.1.4 Chemical grouting. Chemical grouting involves the injection of chemical solutions that react with the soil or groundwater to form a solid mass or reduce permeability. The chemical grout may harden or bond the soil particles together, increasing the strength and reducing the potential for settlement. Materials used: sodium silicate, polyurethane, acrylics. Applications: seepage control in permeable soils, waterproofing, stabilization of loose soils or fractured rock, mitigation of soil liquefaction. 1.3.1.5 Compaction grouting with superplasticizers. This type of grouting technique involves the injection of highly fluid grout mixtures, including superplasticizers, which help to enhance the grout's flowability and increase the efficiency of the compaction process. Superplasticizers allow the grout to penetrate and compact fine-grained soils, such as silts and clays. Materials used: cement-based grout, superplasticizers, additives for fluidity. Applications: deep compaction of fine-grained soils, enhancement of load-bearing capacity, minimization of soil settlement. 1.3.2 Grouting process. The grouting process typically involves several key steps. 1. Site investigation and design. Detailed geotechnical investigations are conducted to determine the soil properties, groundwater conditions, and other relevant factors. Based on this data, the appropriate grouting technique and grout materials are selected. A grout injection plan is developed to determine the depth, pressure, and grout mix proportions for the injection process. 2. Grout injection. The grout is injected into the ground through a series of boreholes drilled into the soil or rock. The grout is injected under controlled pressure and flow rates, ensuring even distribution throughout the target area. In some cases, a series of injection stages may be used to create overlapping grout columns or continuous grout barriers. 3. Monitoring and quality control. The grouting process is closely monitored to ensure that the grout is being injected at the proper rate and pressure. Various testing methods such as grout injection pressure and volume are used to assess the effectiveness of the grouting process. After grouting, quality control tests such as borehole inspection, permeability tests, and compressive strength tests may be conducted to confirm the improvement in soil properties. 4. Curing and final inspection. After the grout has been injected, it is allowed to cure and harden. Depending on the type of grout used, curing may take from several hours to days. Final inspections are performed to verify the extent of improvement and ensure the desired outcomes, such as reduced permeability or increased strength. 1.3.3 Applications of Grouting in Geotechnical Engineering. Grouting techniques have wide-ranging applications in geotechnical engineering. Some of the key applications include 1.3.3.1 Foundation Improvement. Grouting can be used to enhance the load-bearing capacity and reduce the settlement of foundations. It is commonly used for the improvement of weak or unstable soils beneath existing or proposed foundations. Grouting methods such as permeation or compaction. Grouting help increase soil strength, reduce settlement, and prevent structural damage. 1.3.3.2 Groundwater Control and Seepage Prevention. Grouting is often employed in areas with high groundwater levels or water-sensitive soils. It is used to prevent water seepage into excavations, tunnels, or basements, and to create impermeable barriers in dams, levees, or tunnels. Chemical grouting and permeation. Grouting are commonly used to reduce permeability and control groundwater flow. 1.3.3.3 Slope stabilization. In unstable slopes or embankments, grouting can be used to increase the strength of the soil or rock, preventing landslides and improving overall slope stability. Grouting is often combined with other slope stabilization techniques such as soil nailing or geogrid. Reinforcement to enhance the stability of slopes and prevent failure. 1.3.3.4 Seismic hazard mitigation. Grouting can be used to mitigate the risk of liquefaction during earthquakes by increasing soil density and reducing permeability. Grouting helps prevent soil failure and ground deformation under seismic loading. This is particularly useful in loose sands or siltous soils that are prone to liquefaction. 1.3.3.5 Tunnel and shaft construction. In tunnel and shaft construction, grouting techniques are employed to control water ingress and to stabilize the surrounding soil or rock. Grouting is used to create watertight barriers around the tunnel and to prevent ground movement or settlement that could ECT the tunnel structure. Jet grouting is often employed in such applications for deep ground treatment. 1.3.3.6 Sinkhole and void remediation. In areas prone to sinkholes or ground subsidence, grouting can be used to fill voids and stabilize the soil. The grout is injected into cavities, fractures, and voids to solidify the ground, preventing further subsidence and potential surface collapse. 1.3.4 Advantages of grouting techniques. Increased strength and stability. Grouting improves the strength of weak soils, making them more stable and capable of supporting heavier loads. Reduce permeability. Grouting helps to decrease the permeability of soil, preventing the infiltration of water into structures or foundations. Cost-effective. Grouting is often a more cost-effective solution than other methods of ground improvement, especially for large areas or sites with complex soil conditions. Minimal disruption. Grouting is typically a non-invasive method that causes minimal disruption to the surface or surrounding structures, making it ideal for urban construction or sensitive environments. Versatility. Grouting techniques can be adapted to a wide range of soil types and project requirements, including those in complex or challenging geotechnical environments. 1.3.5 Limitations of grouting. Soil characteristics. Grouting may not be active in soils with very large voids, highly fractured rock, or highly permeable materials, where grout may not adequately fill all gaps. Cost variability. While generally cost-effective, the cost of grouting can vary depending on the depth of injection, type of grout used, and site conditions. It may not always be the most economical option for all types of projects. Time-consuming. Some grouting techniques, particularly chemical grouting or jet grouting, can be time-consuming and require careful monitoring to ensure the desired results are achieved. Conclusion. Grouting is a versatile and effective technique for improving soil properties and ensuring the stability of geotechnical projects. The choice of grouting technique depends on the specific site conditions, soil types, and desired outcomes. Whether used for foundation improvement, seepage control, or soil stabilization, grouting plays a key role in enhancing the safety and performance of construction projects in geotechnical engineering. With proper planning, execution, and monitoring, grouting can be a powerful tool for addressing challenging soil conditions and ensuring the success of various infrastructure projects. Chapter 11. Ground Improvement Techniques. 11.4 Geofoam and Geotextile Applications. Geofoam and geotextiles are important materials used in ground improvement techniques, particularly for lightweight soil stabilization, slope stabilization, and reinforcement in various geotechnical applications. Both materials serve distinct purposes but are often used together to enhance the performance of geotechnical systems in different environments. In this section, we explore the properties, applications, and advantages of geofoam and geotextiles in geotechnical engineering, with a focus on their roles in improving the behavior of soil and facilitating safer, more durable infrastructure. 1.4.1 Geofoam. Properties and applications. Geofoam is a lightweight, rigid foam material made from expanded polystyrene, EPS, or other similar materials. Due to its low density and high compressive strength, geofoam is used to address challenges associated with heavy soils, subsidence, and weak ground conditions. 11.4.1.1 Properties of geofoam. Load density. Geofoam has a density ranging from 15 to 45 kilograms per cubic meter, making it much lighter than conventional soil or other geotechnical materials. Its low weight reduces the load on the underlying soil, making it ideal for projects involving soft or compressible soils. High compressive strength. Despite its lightness, geofoam has a high compressive strength to weight ratio, which allows it to support significant loads without deformation. Thermal insulation. Geofoam provides excellent insulation properties, which can be beneficial in projects involving temperature-sensitive materials or underground construction. Water resistance. Geofoam is impervious to water, which makes it suitable for use in drainage-restricted environments. Durability. Geofoam is resistant to chemical degradation, ensuring long-term performance in various environmental conditions. 11.4.1.2 Applications of geofoam. 1. Lightweight fill for soil stabilization. Geofoam is widely used as a lightweight fill material to reduce the weight and stress on underlying soft or compressible soils. Its use is particularly advantageous when traditional fill materials would result in excessive settlement or cause damage to existing structures. Example: in areas with soft soils or where ground improvement is difficult, geofoam is used in embankments or road construction to avoid differential settlement. 2. Slope stabilization. In slope stabilization projects, geofoam can be used to reduce the weight of the slope, thus minimizing the risk of landslides or soil erosion. The foam's low density helps to stabilize slopes without adding significant load to the existing soil layers. Example: geofoam is used in the construction of highway embankments, reducing the risk of landslides and providing long-term slope stability. 3. Bridge approach embankments. Geofoam is commonly used in bridge approach embankments, where it minimizes settlement or movement that could otherwise ECT the alignment and integrity of the bridge. Its low weight reduces the lateral pressure exerted on the bridge foundation. 4. Seismic applications. In earthquake-prone areas, geofoam helps reduce the impact of seismic forces on structures by minimizing ground shaking and settling, providing a flexible solution for infrastructure projects in such regions. 5. Foundation support. Geofoam can be used as a lightweight, low-settlement material for foundation support, especially in areas where conventional fill materials would lead to excessive settlement. 1.4.2 Geotextiles. Properties and applications. Geotextiles are synthetic materials used in geotechnical engineering to provide a range of functions such as reinforcement, drainage, filtration, and separation of soil layers. These Woven or non-woven fabrics are made from polymers like polypropylene, polyester, or polyethylene. 11.4.2.1 Properties of geotextiles. High tensile strength. Geotextiles have excellent tensile strength, allowing them to resist deformation under applied loads. This makes them effective in reinforcing weak soils or providing additional stability to structures. Durability. Geotextiles are resistant to various environmental factors, including UV, radiation, chemical degradation, and biological attack, ensuring their long-term functionality in challenging conditions. Permeability. Depending on the type of geotextile, it can either allow water to pass through, permeable, or resist water flow, impermeable. Geotextiles with high permeability are often used in drainage applications. Flexibility. Geotextiles are flexible materials that can conform to the shape of the underlying soil or structure, making them adaptable to a wide range of site conditions. 11.4.2.2 Applications of geotextiles. 1. Soil reinforcement. Geotextiles are commonly used to reinforce weak or loose soils. When placed between soil layers, geotextiles improve the soil's load-bearing capacity by distributing the applied loads and reducing the potential for settlement. Example: geotextiles are used in the construction of retaining walls, embankments, and roadways, providing reinforcement in areas with soft or unstable soil. 2. Separation of soil layers. In applications where two different types of soil must be kept separate to prevent mixing or contamination, geotextiles are used as a separation layer. This ensures the stability of the construction while preserving the integrity of each soil layer. Example: geotextiles are used in road construction to separate the subgrade soil from the base material, preventing mixing and ensuring better load distribution. 3. Drainage and filtration. Geotextiles are highly effective in drainage applications where water flow needs to be controlled or directed. They act as a filter, allowing water to pass through while preventing soil particles from being carried away, thus maintaining the integrity of the soil structure. Example: geotextiles are used in the construction of French drains, stormwater management systems, and retaining walls to facilitate water drainage and prevent soil erosion. 4. Erosion control. In areas prone to soil erosion, geotextiles provide a protective barrier to prevent the loss of soil particles. They are particularly useful in stabilizing slopes, embankments, and coastal areas by reducing the impact of wind and water erosion. Example: geotextiles are used in slope stabilization and shoreline protection projects to reduce the risk of erosion and improve the long-term stability of the site. 5. Landfill lining and covering. Geotextiles are commonly used in landfill Construction to separate waste from the surrounding soil, prevent contamination, and facilitate the drainage of leachate. They are also used in covering the landfill to reduce the spread of odors and protect against contamination. Example: in municipal solid waste landfills, geotextiles are employed as a part of the liner system to contain waste and prevent groundwater contamination. 6. Pavement design and repair. Geotextiles are used in pavement applications to reinforce the base and subbase layers, reduce cracking, and improve the overall performance and lifespan of the pavement structure. Example: geotextiles are placed between the subgrade and base course in road construction to improve pavement strength and reduce deformation. 1.4.3 Combined use of geofoam and geotextiles. Geofoam and geotextiles are often used together in ground improvement projects to maximize their benefits. The combination of these materials can provide a more effective solution to address a range of geotechnical challenges. 1. Stabilization of embankments. In embankment construction, geofoam can be used to reduce the weight on the underlying soil, while geotextiles provide reinforcement and prevent soil mixing. The combination helps to ensure long-term stability and prevent settlement. 2. Slope protection. Both geofoam and geotextiles are used in slope protection applications. Geofoam reduces the weight on the slope, while geotextiles provide reinforcement and filtration, ensuring that water is effectively drained away and preventing soil erosion. 3. Drainage systems. In drainage applications, geofoam can be used to fill in voids or provide insulation, while geotextiles act as a filtration medium. This combination improves water flow and helps protect the surrounding soil from erosion or contamination. 1.4.4 Advantages of geofoam and geotextiles. Improve soil stability. Both geofoam and geotextiles contribute to the stabilization of soft, loose, or unstable soils by enhancing soil properties and preventing excessive settlement. Cost-effectiveness. The use of geofoam and geotextiles can reduce the need for expensive ground improvement methods, such as soil replacement or deep foundation systems, making these materials an economical choice for many applications. Reduced environmental impact. Both geofoam and geotextiles are lightweight materials that can reduce the need for heavy machinery and minimize disturbance to the environment during installation. Versatility. Geofoam and geotextiles can be used in a wide variety of geotechnical applications, including embankments, slopes, pavements, drainage systems, and foundation support. Conclusion. Geofoam and geotextiles are versatile and effective materials used in ground improvement techniques. Geofoam's lightweight and compressive strength make it an ideal material for reducing the load on weak soils, while geotextiles serve a wide range of functions, including reinforcement, filtration, and drainage. Together, these materials can improve soil stability, reduce environmental impacts, and provide cost-effective solutions for a wide variety of geotechnical applications. The combined use of geofoam and geotextiles is an essential aspect of modern geotechnical engineering, helping to ensure the success of infrastructure projects in diverse environments. Chapter 11: Ground Improvement Techniques. 11.5 Advances in Ground Improvement Technologies. Ground improvement techniques have significantly evolved over the years, driven by the increasing demand for more efficient, cost-effective, and sustainable solutions in geotechnical engineering. Advances in material science, construction techniques, and technology have expanded the range of methods available for improving the properties of soils, stabilizing weak or problematic ground, and enabling the safe construction of infrastructure in challenging environments. In this section, we discuss the latest advancements in ground improvement technologies, including innovative methods, tools, and materials that are transforming the field of geotechnical engineering. 1.5.1 Advances in Soil Stabilization Methods. Soil stabilization methods have seen significant technological advancements, offering more efficient and environmentally friendly ways to improve soil properties. Modern stabilization techniques not only enhance the mechanical strength of soil, but also address issues like environmental sustainability and cost-effectiveness. 1.5.1.1 Use of geopolymers and sustainable binders. Geopolymers and sustainable binders, such as fly ash, slag, and natural pozzolans, are gaining popularity as alternatives to traditional cement for stabilizing soils. These materials have lower carbon footprints and similar, if not superior, strength characteristics compared to conventional stabilization methods. Geopolymer stabilization. Geopolymers are made from industrial byproducts like fly ash or slag mixed with alkali activators. These materials form strong, durable bonds when mixed with soil, improving its load-bearing capacity and reducing its susceptibility to water erosion. Sustainable binders, incorporating industrial waste materials in soil stabilization, such as fly ash or cement kiln dust, reduces the environmental impact of construction projects and provides an eco-friendly solution to soil improvement. 1.5.1.2 Nanotechnology in soil stabilization. Nanotechnology has brought about innovations in soil stabilization by introducing nanoparticles into soil matrices. These nanoparticles can enhance soil structure, increase its strength, and reduce permeability. Nanosilica and nanoclay materials, for example, have been shown to significantly improve the mechanical properties of soil when applied at small dosages. Nanosilica stabilization. When mixed with soil, nanosilica particles fill in the micropores of soil grains, increasing the cohesion and strength of the soil. Nanoclay stabilization. Nanoclay particles improve the cohesion and overall stability of fine-grained soils, offering potential solutions for foundation engineering in weak or problematic soil conditions. 1.5.2 Deep soil mixing and vibrocompaction. 1.5.2.1 Innovations in deep soil mixing (DSM). Deep soil mixing (DSM) is an advanced technique for improving the strength and steadiness of weak soils by mixing them with binding agents such as cement or lime at greater depths. Recent innovations in DSM focus on improving the efficiency and precision of this method, making it applicable to a wider range of soil types and depths. Automated and precision DSM. New automated DSM systems enable greater precision in the mixing process, improving the homogeneity of the soil cement columns and enhancing the overall performance of the technique. Hybrid DSM techniques. Combining DSM with other techniques, such as jet grouting or soil nailing, results in hybrid systems that can achieve superior soil improvement, especially in challenging or non-uniform soil conditions. 1.5.2.2 Vibrocompaction advancements. Vibrocompaction is used to densify loose or granular soils, improving their bearing capacity and reducing settlement. Recent advances in vibrocompaction technologies include high-efficiency vibroflotation. The introduction of high-efficiency vibroflotation equipment has improved compaction depth and reduced energy consumption, making it possible to treat deeper layers of soil with fewer resources. Vibro replacement with geosynthetic reinforcement, integrating geosynthetics with vibro replacement techniques has improved the effectiveness of deep foundations by providing additional reinforcement to the treated soils, making them more resistant to settlement under loading. 1.5.3 Ground freezing and thermally induced ground improvement. Ground freezing is a technique that temporarily solidifies soil by lowering its temperature, creating a frozen barrier that can provide support during excavation or construction. Recent advancements in ground freezing techniques focus on reducing energy consumption and enhancing the speed and reliability of the freezing process. 1.5.3.1 Energy efficient ground freezing systems. Innovative ground freezing systems now use more energy-efficient refrigeration methods, reducing the overall carbon footprint of the process. Additionally, the use of liquid nitrogen and carbon dioxide has improved the speed at which freezing can be achieved, making it a more viable solution for urban projects or areas with sensitive ecosystems. Closed-loop freezing systems. Advances in closed-loop freezing systems allow for the reuse of refrigerants and cooling fluids, resulting in more efficient and sustainable ground freezing processes. 11.5.3.2 Thermally induced ground improvement. Another exciting development is the use of thermal methods for soil improvement. By introducing heat into the ground, certain soil properties can be modified to achieve more favorable engineering conditions. Thermal treatment of expansive soils. Heating expansive soils can reduce their swelling potential and improve their stability, offering a promising solution for foundations in clayey soils prone to volume changes. Thermally assisted ground improvement. This technique is combined with other methods like grouting or compaction to accelerate soil stabilization, particularly in challenging conditions where conventional techniques may be inefficient. 1.5.4 Geosynthetic reinforcement and composite systems. 1.5.4.1 Advanced geosynthetic materials. Geosynthetics, which include geotextiles, geogrids, geocells, and geomembranes, have seen significant advancements in material properties and applications. Modern geosynthetics are designed with improved durability, load-bearing capacity, and flexibility, making them even more effective in ground improvement projects. High-strength geogrids and geotextiles. The development of high-strength, thermally stable geosynthetics has enhanced their performance in soil reinforcement, especially in retaining walls, embankments, and foundations. Composite geosynthetic systems, combining different geosynthetic materials, such as geotextiles with geogrids or geomembranes, has resulted in composite systems that deliver superior soil stabilization, drainage, and filtration properties. 1.5.4.2 Geocell reinforcement technology. Geocells, a type of 3D honeycomb-shaped geosynthetic material, are increasingly used for soil stabilization, slope reinforcement, and erosion control. Advances in geocell technology have improved their flexibility, strength, and ease of installation. High-strength geocells. Recent developments in high-strength polymer materials have made geocells more durable and capable of withstanding heavy loads, increasing their use in a wide range of ground improvement applications. Geocell-enhanced pavement systems. Geocells are being integrated into pavement systems to improve load distribution and prevent cracking, especially in areas with poor soil conditions. 1.5.5 Remote sensing and monitoring in ground improvement. The use of advanced remote sensing technologies and monitoring tools has revolutionized the field of ground improvement by providing real-time data on soil behavior, material properties, and the effectiveness of improvement methods. 1.5.5.1 Geophysical monitoring techniques. Innovative geophysical methods, such as ground-penetrating radar, GPR, and electrical resistivity tomography, ERT, are increasingly being used to monitor the effects of ground improvement techniques in real time. These methods provide detailed insights into the soil structure, allowing engineers to assess the effectiveness of treatments and make adjustments as needed. Real-time monitoring, advanced monitoring systems that integrate sensors, data acquisition systems, and remote sensing technology allow for continuous tracking of soil conditions, helping to detect any changes or failures in ground improvement systems. In situ testing innovations. Modern in situ testing techniques, such as cone penetration testing, CPT, and pressure meter tests, provide real-time data on the behavior of soils under various loading conditions, helping engineers to refine their ground improvement strategies. Conclusion. Advancements in ground improvement technologies are transforming the landscape of geotechnical engineering. From sustainable soil stabilization methods to cutting-edge geosynthetic applications and innovative monitoring techniques, these technologies are enabling more efficient, reliable, and environmentally friendly solutions for addressing complex geotechnical challenges. By leveraging these advancements, engineers can provide more effective ground improvement strategies that ensure the stability and sustainability of infrastructure projects worldwide. As these technologies continue to evolve, they will play a critical role in shaping the future of geotechnical engineering. Thank you for your attention in watching this video lecture on the Triune Biblical University Global Extension USA channel. Kindly like, share, subscribe, and comment to help us bring more educational content your way. The link to the next part of this video will be posted in the description section.